Today, we're cracking open a cosmic cold case, Messier 103. Now, this isn't just any old star cluster. It's the very last object that Charles Messier himself put into his famous catalog, which makes it a really special piece of astronomical history. And, like any good mystery, its sparkly appearance hides some absolutely fascinating secrets. So what is this cluster hiding? I mean, how old is it? How far away is it really? Well, to find out, we have to become cosmic detectives. We're going to have to gather clues that are literally written in starlight and sift through what turns out to be a very crowded cosmic crime scene. And here it is. This is our subject, Messier 103. It's this beautiful, kind of loose gathering of stars about 9,400 light-years from us, just hanging out in that familiar W shape of Cassiopeia. It looks pretty straightforward, right? Well, looks can be deceiving. Okay, so our investigation starts with the single biggest challenge that astronomers face when they're looking at something like this. I like to call it the cosmic photobomb problem. And that problem is contamination. You see, the galaxy is an incredibly crowded place. When we look out at Messier 103, we're not just seeing its member stars. We're looking through this thick curtain of thousands of totally unrelated field stars. Some are closer, some are way farther away. They just happen to be in our line of sight. It's kind of like trying to take a family photo in the middle of a packed train station. How do you figure out who actually belongs in the picture? So, to get around this cosmic photobombing, our detectives need to gather some very specific clues. Let's take a look at the forensic toolkits they use. They've got two main techniques. First up, the proper motion study. Since all the stars in Messier 103 were born together, they travel through the galaxy together, kind of like a flock of birds. So by comparing pictures taken decades apart, astronomers can track each star's tiny little movement. The ones moving in formation, those are the real family members. Then, for the fainter stars, they use something called statistical subtraction. They take a picture of a nearby, boring patch of sky to get a sample of the background crowd, and then they digitally subtract that pattern from the main image, hopefully leaving just the cluster behind. Now, this idea of proper motion is absolutely crucial. It's not about a star moving toward us or away from us. It's its slow, sideways drift across our line of sight. And this movement is unbelievably subtle. We're talking measured in milli-arcseconds per year. To put that in perspective, that's like measuring the width of a human hair from over 10 miles away. But that tiny motion is the unique fingerprint that tells us which stars are traveling together. And check this out. This plot shows you exactly what that data looks like. See all those dots scattered everywhere? Those are the photobombers, the field stars, all going their own way. But look, right in the middle. You see that tight, dense clump? That's it. That's Messier 103. Those are the stars moving in perfect unison. It's the clear signature of a true cluster. The case is really starting to come together. All right, so now that we've identified the true members of the Messier 103 family, we've kicked out all the photobombers, we can finally start analyzing the real clues to figure out its age and its true distance. And the main tool for this part of the job is the color magnitude diagram, or a CMD. You can basically think of this as our investigation board. We plot every single star based on its brightness, or magnitude, and its color, which tells us its temperature and gives us big hints about where it is in its life. And this is what the board looks like before we clean it up. It's a complete mess, right? This plot has every star we can see in the area, both the cluster members and all those field stars. It's just a noisy scatter of points. Trying to find a clear pattern in here is pretty much impossible. But then, once we use our proper motion data to filter out all those unrelated stars, something really amazing happens. All that noise just vanishes, and a clear, distinct shape starts to take form. We can finally see the true structure of Messier 103. So how do we get a precise age from this pattern? Well, we use this super cool technique called isochrone fitting. Astronomers have these powerful computer models that can predict what a star cluster's CMD should look like at all sorts of different ages. An isochrone is just a curve that represents a bunch of stars all born at the same time. The detective's job is to find the one theoretical age curve that perfectly fits our evidence. And here it is, the aha moment. This is our cleaned-up evidence board for Messier 103, with a theoretical isochrone laid right on top. Just look at how perfectly that red line traces the main group of the cluster's stars and that turn-off point for its brightest members. The model that fits this well, it corresponds to a very specific age. The code has officially been cracked. So, The verdict is in. The analysis shows that Messier 103 is about 16 million years old, give or take about 4 million years. And to put that in perspective, that is incredibly young for a star cluster. I mean, these stars showed up long after the dinosaurs went extinct. And the same model that gives us the age also nails down the distance. It confirms Messier 103 is located 2,884 parsecs away. A parsec is just another cosmic yardstick. It equals about 3.26 light years. So that puts the cluster right around 9,400 light years from us. Case closed on the basic stats. But just as our detectives were packing up their files, they noticed something they hadn't seen before. Something on the original photographic plates. A clue that opened up an entirely new and maybe even more intriguing case. You see, on the edge of the very same images they used to investigate Messier 103, they found another, smaller star cluster. It's named Trumpler 1. At first, it was just a neighbor, but they decided, just to be thorough, let's run its fingerprints too. Now this is where it gets really cool. Take a look. On the left is the proper motion plot for Messier 103 we've already seen. On the right, that's the plot for its neighbor, Trumpler 1. I mean, the resemblance is just uncanny. They both show that tight group of stars moving in lockstep, and they're moving in the exact same way. And it's not just our eyes playing tricks on us. The hard data totally confirms it. This table shows the average proper motion for both clusters. Now, the numbers aren't perfectly identical, but statistically, within their margins of error, they are the same. This means from where we're sitting, both of these clusters are cruising through the Milky Way in the same direction at the same speed. So let's just review the evidence here. We have two separate star clusters, Messier 103 and Trumpler 1. They're at roughly the same distance from us. Other studies tell us they have similar ages. And now we know for a fact they are traveling through the galaxy together on a parallel path. That is a heck of a lot of coincidence. Which leads us to our final huge question. Could this be some kind of cosmic partnership? Is it possible that these two clusters aren't just neighbors, but are actually a super rare binary star cluster, gravitationally bound together and journeying through the galaxy as one system? The investigation into one object has suddenly uncovered a potential relationship that leaves us with an even bigger and way more exciting mystery to solve.